Good morning. I'm Mike Griffin, and I'm here to introduce our speaker for today's Aeronautics Research Mission Directorate Technical Seminar. Our seminar today is on the topic of oil-free turbomachinery technology for rotorcraft propulsion and advanced aerospace propulsion and power. The oil-free part got my attention. The last time I tried that in an airplane, it resulted in a landing in a plowed field. So presumably there have been some advances made in oil-free lubrication. And we're going to hear about those from Chris Delacourt, Dr. Chris Delacourt, who is a materials research engineer at NASA's Glenn Research Center, concerning the development path and supporting research to apply oil-free bearing technology in future engines, especially rotorcraft engines. Now, I think all of you, either here or listening out there, know that conventional bearings, which are lubricated with oil, can limit the speed, temperature, and life of aircraft engines, APUs, auxiliary power units, and various power generation turbines of many kinds. These bearings don't work efficiently at the high speeds that we need new engines to work at. Rotorcraft engines are among the most demanding applications for these bearings because they have to operate with extreme reliability and the very highest possible power density. In the future, it may be possible to deploy oil-free turbomachinery systems that weigh less and cost less to operate, thanks to breakthroughs in gas-lubricated foil bearings, high-temperature solid lubricants, and computer-based modeling. These breakthrough technologies, if we can get them, will benefit rotorcraft, but they will also benefit supersonic, hypersonic flight, and long-lived space nuclear power generators. Chris Delacourt is NASA's principal investigator for rotorcraft propulsion, incorporating oil-free turbines for advanced systems. He leads the oil-free turbomachinery team at GRC and is working with industry and academia on the development of oil-free turbine propulsion and power systems. He's an expert in tribology and in mechanical systems for space and aeronautics applications. He's published extensively on the wear and friction of materials at high temperatures and holds 3 patents for novel high-temperature solid lubricant technology. He's worked at Glenn since 1985. In 1999, his efforts resulted in the world's first demonstration of an oil-free turbocharger for heavy-duty diesel engines, and it's now being commercialized. He's also successfully transitioned his PSPM 300 solid lubricant technology to industry. He received his doctorate in mechanical engineering from Case Western Reserve, and we're proud to have him at NASA. I'd like you to welcome Chris Delacourt.
Thanks a lot, Mike.
Thanks, Chris. Good to see you.
And thank you for coming out. And those of you that are at the NASA centers listening via the link, thank you for taking the time out of your busy schedules to hear what I have to say. That was quite an introduction, and I really appreciate it. You kind of set the stage for what I'm going to be talking about today. First off, I will say that Administrator Griffin was right. When we talk about oil-free turbine engines, we're not talking about just draining the oil out of your aircraft engine or car engine and running it as usual. This is not a snake oil salesmanship job. We're talking about developing all new technologies for all new engines. But one other preface before I get started. The word tribology may come up during the presentation. It's a word that may be foreign to many of you. It's a fairly new term, only about 30 years old. It's a term that we coined ourselves in the field to represent friction, wear, and lubrication. So if you hear me talk about tribological coatings, you know I'm talking about high-temperature solid lubricants, advanced oils, those kind of things. So with that, I think I'd like to get started. If you could go to the first chart, please, I'd appreciate that. The presentation really centers on oil-free turbomachinery. For the last several years, we've been concentrating in the small engine arena for rotorcraft propulsion, and this technology has been around for quite some time. We also have applications in advanced aerospace propulsion and power. So you'll see references to past work where we've worked on business jet engines, we've worked on turbochargers, auxiliary power units, and recently in space power Brayton systems. I'd like to start off by acknowledging the generous support that we've gotten from NASA's Fundamental Aeronautics program, and especially the Subsonic Rotary Wing Project, which is where we're doing most of our work today. Next chart, please. The general outline of this presentation is as follows. I'm going to be doing a little bit of a background tutorial, if you will, on rotorcraft propulsion challenges, because the challenges in rotorcraft propulsion are very unique compared to other flight regimes. And weight, I'll tell you right now, weight is a critical issue. I'm going to be talking about developing a new concept called the optimized propulsion system, which really opens up the architecture trade space for future rotorcraft. And I'll talk about the oil-free engine technologies that make the optimized propulsion system possible. I'll spend probably most of my time talking about oil-free engine technologies, and I'll be talking about the three key technologies, foil air bearings, high-temperature solid lubricants, that protect those bearings during startup and shutdown periods, and the computer and analytical-based modeling that we do to try to integrate these three key technologies. Then I'll review some recent technological accomplishments to try to give you a flavor for what is the technology development path from first concept to laboratory work to first demonstrations and finally commercialization. And then I'll touch on where this technology helps the other part of NASA in the space power generation arena. And then I'll wrap up by talking future prospects and conclusions. Next chart, please. And another way to put this outline is what I call the technology circle. If you think about it, at the top of the chart, we've got flight vehicles. That's our Cleveland Metro Health Center rescue helicopter. That flight vehicle is supported by a propulsion system. And on the left of the chart, you see the propulsion system photograph of a turbine engine, which is used for its high power to weight ratio. And that turbine engine drives a gearbox that reduces the high turbine shaft speed to the low rotor speed needed for the helicopter, efficient helicopter operation. And what we're trying to do is develop technologies that allow us to optimize that propulsion system. And that cartoon at the 6 o'clock position on the chart shows an engine on the right-hand side, which we're trying to make oil-free by taking the oil out and putting air bearings in, and then developing a specific multi-speed transmission that together form the optimized propulsion system. And the way we do the optimized propulsion system engine, the oil-free engine, is to adopt oil-free technologies, and the photograph there are some foil air bearings and specialized shafting that are put into those bearings. So when I go through this presentation, and I'm going to be spending time on the oil-free technologies, think about how those technologies feed into the optimized propulsion system that then go into future flight vehicles. Next chart, please. Now, NASA's goal for rotorcraft is to radically improve the civil benefits of rotary wing vehicles. We're really talking about improving ease of access, reducing congestion at airports, enhancing the capabilities of emergency and rescue services. Propulsion has an opportunity to make a contribution to this NASA goal. And when I talk about propulsion's contribution, I'm talking about developing tools, concepts, technologies, all aimed at enabling a lightweight, fuel-efficient, multi-speed rotorcraft, enabling new rotorcraft architectures. And when I talk about multi-speed rotorcraft, I'm talking about the ability of a rotorcraft to do vertical lift and faster forward flight than we can currently do. The approach that we're taking to come up with these new propulsion systems to help NASA achieve this goal is to combine emerging oil-free technology engines with high power density, multi-speed or variable speed transmissions in terms of that optimized propulsion system I talked about before. Next, please. This is the chart that I dub Rotorcraft Propulsion 101. It's worthwhile to go over for just a moment here and remind everybody that unlike a fixed-wing aircraft, which gets its lift from the wings themselves, a rotorcraft gets its lift from the rotary wing, which means the propulsion system has to provide all of the power for lifting, all the power for propulsion, maneuvering, and it has to do this at all times. There is no point in a mission flight of a rotorcraft that it can just kind of coast or glide in for a landing. The engine and transmission system has to be there all the time. And it turns out that the total weight for a rotorcraft propulsion system, that being the engine and the drive system, and you can see on the chart the engine on the left, at the lower left, added with the transmission or the gearbox, equals 25% of the total weight of the rotorcraft. That 25% is a very large number. It's at least twice the total weight of the propulsion system in your traditional fixed-wing aircraft. What that means in performance terms is that everything we can do as propulsion system designers to reduce the weight of the propulsion system pays enormous dividends and benefits in enabling capabilities of the rotorcraft, more so than a fixed-wing aircraft. So if we can cut weight out of the propulsion system, we can do a lot more. Next chart, please. So rotorcraft engines, they need to be lightweight, they need to be efficient, they need to be ultimate in reliability. They also need to be affordable. They spend a lot of time flying close to the ground, rotorcraft do. They kick up a lot of dirt and debris, so the engines have to be very debris tolerant. And going hand in hand with debris tolerance is high durability, especially in rotorcraft engines, which tend to be smaller than your traditional fixed-wing aircraft. Internal engine clearances, for example, damage due to sand ingestion and erosion can degrade performance more so than a large engine. So durability and debris tolerance are critical issues. Next, please. The transmission, very similarly, needs to be lightweight, efficient, and reliable. The current state of the art for transmissions in rotorcraft are that they're single-speed gearboxes. There's no multi-speed transmissions, and this is really so that you can have a very lightweight system with a typical gear ratios of about 100 to 1. You've got to reduce the RPM of the engine to a very low RPM to have efficient rotary wing operation. Another aspect of rotorcraft transmission that most people don't realize is that rotorcraft transmissions, by and large, don't use transmission fluid like your automatic transmission in your car. They don't use gearbox oil like a stick shift transmission in your car might use. They actually use engine oil. And rotorcraft do this to try to avoid carrying two oil systems, one for the engine, one for the transmission. So if you think about how we might change rotorcraft transmissions, we're looking at things like multi-speed transmissions, and we're looking at transmissions that can be optimized and operate on gear oil. And I'll touch on that some more in the future, in the next charts as well. Next chart, please. What do we want to do? Why do we have new challenges in rotorcraft propulsion? Well, these artist conceptions here are different rotorcraft architectures that we would like to develop to achieve things like faster forward flight, to achieve larger rotorcraft vehicles with more payload, with reduced operating costs. And we're looking at things like quad rotors, tilt rotors. In fact, the larger picture on the right in the center is the artist's conception of the large civil tilt rotor. The concept is to have like a 737 class vehicle that can take off vertically and fly at fast forward speeds. These types of vehicles require new propulsion systems. Next chart, please. So we want to achieve faster forward flight. We want to improve rotorcraft capability, but of course we don't want to pay anything for it. We want to maintain efficiency. We don't want to increase noise. This really translates to challenges for the propulsion system in ways that aren't immediately obvious. For example, we need to maintain a very high rotor RPM for doing vertical lift and hovering. But when you're flying your rotorcraft at a fast forward flight conditions, you need to be able to slow the rotor down so that you have a higher propulsive efficiency. Unfortunately, the typical state-of-the-art propulsion system is only efficient over a narrow operating range of rotor RPMs. So we need to develop technologies to provide a wide range of rotor RPMs at high power levels without increasing weight or increasing complexity. Next chart, please. And one of the ways we're planning to do this is to develop a multi-speed transmission. This is really going to be enabling for advanced aircraft. And it may not seem like very much of a challenge to the rest of the world because we drive cars every day that have 3, 4, 5, even 6 or 7 speed automatic transmissions. We've been doing it for decades. It shouldn't be that hard conceptually to develop a multi-speed transmission for a rotorcraft. But think about this. In your car, the way you achieve shifting from one gear to another is that the engine and transmission momentarily decouple and the car coasts for a brief instant while the gears change and you get a nice smooth shift. But you can't really do that in a rotorcraft because you've got to be providing high torque levels to the rotor at all times to keep the rotorcraft lifted. So shifting is a real challenge. How would you shift a variable speed transmission? And we've got folks in our transmission group that are working on those concepts now. So we want to develop these multi-speed transmissions. We want to minimize weight penalties. And we really don't have a whole lot to go on in terms of precedence in large rotorcraft. So think about what we need to do in the balance of the propulsion system to maybe reduce the weight in the engine so that we could give the transmission designers a little bit more latitude in developing these advanced transmission designs. Next chart, please. I mentioned this before, and this chart kind of hammers the point home. Today's rotorcraft have a shared oil system. The turbine engine oil supply is used for both the transmission and the engine to reduce weight. If you had to carry a separate oil system for the engine and a separate oil system for the transmission, the rotorcraft propulsion system would get too heavy. This has a tendency to compromise the transmission performance. The engine conditions dictate a thin oil with special additives to protect the oil at high shear rates in the bearings and high temperatures. It also precludes the use of gear-specific oil additives, the sulfur-containing compounds that we typically use in gears to be able to run them at highly loaded conditions. If we're going to develop multi-speed transmissions, we are most certainly going to need a gear-specific oil to meet standards. Next chart, please. In terms of the engines, rotorcraft engines are optimized for operating at one design speed. There are technologies available to expand the speed range, things like compressor flow control, variable geometry turbine hardware. These types of hardware add weight and cost. So if you were to approach a new rotorcraft propulsion system with the thinking of a single speed gearbox, but an engine that you could throttle back and forth, you're going to wind up with a weight penalty and a cost penalty. So not only do we want transmission technologies that are lightweight and robust and multi-speed, but we need engine technologies that are higher power density, which means higher speed, and higher efficiency, which usually means higher temperature. So fast and hot are what we're looking for in an engine technology. Well, it turns out that the oil-free engine technology meets these requirements, enabling an optimized propulsion system. Next chart, please. The optimized propulsion system, put simply in this chart, shows on the right a turbine engine not supported by traditional oil-lubricated ball bearings and roller bearings, but rather supported by oil-free foil air bearings, coupled to that high power density multi-speed transmission, which gets the benefit of using its own gear oil that's tailored for the transmission. That's what we're talking about as an optimized propulsion system. The question is, can you really build an oil-free turbine engine to make this dream a reality? Next chart, please. Well, in the oil-free research team at NASA, we have our own kind of sub-project goal, and that is to revolutionize aviation, enhance access to space, and we're going to do this through the development of enabling oil-free turbomachinery propulsion and energy systems. We've kind of set the bar pretty high, and I hope by the end of this presentation you'll agree with me that bar is achievable. When I talk about oil-free turbomachinery, I'm defining oil-free turbomachinery as any high-speed rotating system or equipment that operates without oil-lubricated rotor supports. Because when you have a shaft and you want to support that on a system of supports, it's not just a bearing, but you have to have dampers to tame vibration. If you have oil in the system, you've got to have seals. Even if you don't have oil in the system, sometimes you need gas path seals. So we're talking about a whole system that we're trying to develop called oil-free turbomachinery. And the approach that we're taking is to combine breakthroughs in foil air bearing performance, tribological coatings, there's that word, but you already know what it means, and analytical and computational modeling to enable these high-speed, high-temperature, oil-free turbomachinery systems. Next chart, please. This is the oil-free turbomachinery application path. This is where oil-free turbomachinery has been, where it is today, and where it's going. Starting up at the top left, we have a box there for air cycle machines. These are the cabin pressurization compressors that are used to provide clean, cooled, and compressed air on all commercial aircraft today. They're all operating on high-speed shaft systems and with compressor wheels supported on foil air bearings. That technology, which was actually an outgrowth of the earliest space power turbines that were developed on foil bearings, that technology hit the markets in the early 70s. The early 80s saw the extension of that technology to lower temperatures, cryogenic temperatures, in terms of turbo compressors. In the 90s, we helped extend that technology to oil-free turbine generators, microturbines, which give low emissions, low weight, and maintenance-free operation. More recently, we're seeing oil-free turbochargers hitting the streets where you get the benefits of lower emissions and higher operating temperatures. And the two boxes on the right, which have dashed lines surrounding them, that's where we're working right now. We're working small engine technology and eventually mid and large engine technologies as well. Next chart, please. And here's what makes it possible, the three key technologies. Advanced foil gas bearings, where we've seen a doubling in load capacity, and that little picture of a foil bearing, the yellow picture, is a cross-section of a shaft bearing which shows the major elements, and I'll talk about that in a moment. High-temperature solid lubricant coatings that allow the bearings to endure a little bit of rubbing contact during startup and shutdown. When the speeds are low, there's not enough air pressure, the bearings do a little bit of rubbing, and we have to protect them. We've invented some coatings at NASA, like the NASA PS304, and I'll talk about that. And finally, it's not enough to just have bearings and coatings. You've got to know how to use them. So we've spent a lot of time and put a lot of investment into analytical and rotordynamic modeling to try to predict how this technology is going to work and how to avoid high risk, the sort of a hardware approach that you just go in the lab, break hardware, and then scratch your head and try to figure out what went wrong. Next chart, please. This chart says probably 90% of what you need to know about a foil gas bearing. The image on the right has call-outs to talk about the different parts of a foil bearing. You've got the top foil, which is a thin piece of sheet metal that wraps around the shaft, and I've got a bearing in my hand here. I hope the guys can pick it up. But we've got a piece of sheet metal foil. It's a flexible membrane made out of Inconel superalloy foil. And that wraps around a rotating shaft, and the top foil is supported by a piece of corrugated bump foil. It looks like the center layer in a piece of cardboard box. And that's actually a spring pack. It allows a little bit of elastic support for the inner foil, but allows for misalignment and distortion. And the way the bearing operates is that the shaft rotating is actually a viscous air pump. So the air molecules in this room are the lubricant for the bearing. The air molecules stick to the surface of the bearing, and when the shaft rotates, the shaft drags air molecules around, sort of a boundary layer effect, generating a circulation or wind pattern, if you will. And the foil surface is brought very close to the shaft, generates its own hydrodynamic self-acting air pressure, and actually the foil gets pushed off the surface and it floats on air. So these, and I'll pass these around so you can get a feel for what they are and what they do. I've got this half foil here and a full foil bearing. Oh, thanks a lot, Stephanie. The benefits of this technology are that the bearings are self-acting. You don't have to pressurize them from the outside to support the load. They generate their own pressure. There's no speed or temperature limit. In a ball bearing, the balls, as they rotate around a shaft, they centrifugally load the outer race and eventually overload the outer race. These bearings don't have any rolling elements and no centrifugal loading of an outer race, so there's no speed limit. We're not using any oil, so we can run temperatures easily, 12, 13, 1400 Fahrenheit. And because we're using air as the lubricant, we don't need engine oil. Now we can dedicate the oil system on a rotorcraft to gear oil for the transmission. That bump foil that's on the bearings allows for some compliance in the bearing that help the bearings tolerate shaft misalignment, centrifugal stretch of the shaft, things of that nature. And if you do the solid lubricants properly to protect the bearings during startup and shutdown, the bearings essentially last the life of the engine and there's no maintenance. Next chart, please. Now, they say that a picture's worth 1,000 words. Certainly I'm passing around some parts and you can get a feel for a foil bearing. I brought two things with me that would help out even further. I've got an animation that I'm going to show in a moment that shows the assembly of the foil bearing, and we'll put it through its paces, a few start, stop, and load cycles, and you'll see how it works. And after the presentation is over, I've even brought a working bearing prototype with me, and those of you that are here at headquarters will get a chance to try that out. If I could ask the fellows downstairs to start that animation movie, that'd be very helpful. So here's our foil bearing assembly. Top foil is what traps the air film. The top foil is tack welded to the structure of the bearing on one end and free at the other. It's supported by that bump foil. That's what gives it spring compliance. There's the shaft, which is that viscous air pump, and then the sleeve is just what you connect the bearing to the rest of your engine structure. So there's a fixed end, and there's also a free end. The other end of the foils are free, and that free end allows the foils to move around and expand as the gas film forms. Now, gas or air enters the bearing at the air inlet. That's going to be pointed out here in just a second. So the air molecules stick to the surface of the shaft and get dragged into the bearing by the rotation of the shaft. It's going to start up here, get a little bit of a rub, the gas film develops, and when the gas film develops, it pushes and flattens out those bump foils. And the foils actually get a little longer at that inlet location. You get a little bit of sliding between bumps and foils. During startup and shutdown, there's a little bit of a rub. You get the gas film formation. Now you're floating on air. There's no touching, there's no wear, and there's no oil system. Under load, the gas film gets a little thinner, the bumps flatten out, but you design it in such a way that you don't have a rub during a high load event. Now during the load and unload cycle, which might happen due to shaft vibrations, you get a lot of rubbing that goes on between bumps and housings, and that gives you friction damping that helps tame vibrations in systems. And finally, during shutdown, you lose the gas film, you get a little rub. Next chart, please. So the question is kind of begged, well, if this technology has been around since the 70s, what's new now? Well, this chart shows a modern technology bearing. The ones I've been passing around, the bump foils are all the same pitch and height, and they look the same everywhere. In fact, a cross-section through the bearing tells you the entire geometry. What's new now is that we have intelligent elastic structural designs. If you look at this picture here, it's a bump foil in the lower left, which shows that the bumps are slit in the axial direction, that's up and down. Circumferentially, the bumps are none of them are the same height or the same length. And the designers have figured out how to tailor the elastic design to give us a thicker gas film, less side leakage of the gas pressure, which gives us more load capacity. They can tailor the stiffness to allow for a known amount of misalignment and distortion. And they've even figured out how to enhance damping characteristics by changing the bump geometry. The upside is that modern bearings exhibit about a 3x improvement over the original designs. And this allows us to put them into more strenuous and challenging turbomachinery systems. Next chart, please. This is one of the key characteristics you need to keep in mind. This is a load capacity versus shaft speed of a foil bearing. Remember, the shaft is a viscous air pump. So the faster the shaft spins, the more air pressure you generate. The good news is the faster you go, the more load you support, and there's no speed limit. The downside to that is that this technology has an Achilles heel, and that is at low speeds and during startup and shutdown, the gas film is inadequate, and you need to provide some solid lubrication, some advanced tribology. I needed to work that word in one more time. Next chart, please. Here's some numbers that we've generated and some rules of thumb that we've generated. This is our rule of thumb for load capacity, and put simply, a journal bearing, like the one I'm passing around, will support about a pound of load per square inch of projected bearing area. That's length times the diameter, per inch of bearing diameter per 1,000 RPM. And put algebraically, like you see on the chart, the load capacity is equal to a coefficient, which we have determined is about 1 for advanced technology bearings, multiplied by the L times D, that's basically the size of the bearing, and then multiplied by the dN, where N is the shaft speed in thousands of RPM. So if you look at that algebraic equation, you can see the dN is the shaft speed, so faster is better, and the L times D is the bearing size, so bigger is better. And when we actually measure bearing performance in the lab, the first line of that data chart is for a 1-inch long by 1.5-inch diameter bearing spinning at 50,000 RPM. That was a bearing from our oil-free turbocharger. It'll support 50 pounds, which is about what you need for a turbocharger. But our colleagues in industry have built bigger bearings. 3 by 4-inch bearing at 20,000 RPM supports over 1,000 pounds. And that's what's shown on the chart on the right. Just shows the load capacity in PSI, or pounds per square inch, as a function of bearing speed. We've extrapolated this load capacity to state-of-the-art bearings. Right now, the biggest bearings that are in laboratory stages are about 6 inches in diameter. 2 6-inch by 6-inch bearings on a shaft provide more than adequate load capacity for a rotorcraft engine or even a regional jet engine. So we're learning how to model the bearings, and the bearings are proving that they behave in a physics-based way, the way we would expect. Next chart, please. Now, foil bearings don't just come in the journal variety. The journal bearings are designed to support shaft motion radial loads. We also have what we call thrust bearings. Thrust bearings, like the one shown on the right, are flattened out versions of the journal bearings, and they're designed to operate against a disc to control axial movement of the shaft. The cartoon at the top is a cross-section of our oil-free turbocharger. It has two journal bearings supporting the shaft in the radial direction, sort of controlling its motion in the bounce and oscillatory modes. The thrust bearing sits on a disc in the center, and it controls the shaft motion axially. Next chart, please. Referring again back to this load capacity characteristic, at zero speed, you've got zero air pressure. You need to provide some solid lubrication for long life. Next chart, please. And that brings us to our second key technology, enabling technology, high-temperature solid lubricants. Now, you can use polymer materials like Teflon or molybdenum disulfide or graphite to lubricate foil bearings if they're never going to see high temperatures. But in turbine engines, we want to run bearings very, very hot. So we had to go out on our own and invent some solid lubricants that could tolerate the engine environment from cold starts all the way up to 12, 13, 1400 degrees Fahrenheit. And we came up with the NASA PS304. NASA PS304, it's a shaft coating. I've got a shaft, and I'll pass this around in a moment, that shows the different methods we use to make the coating. But the coating goes on the shaft and operates against the bare superalloy Inconel foil. The PS304 was designed and tailored just for foil bearings to provide friction and wear protection. It contains a nichrome binder, a chrome oxide hardener, a high-temperature lubricant, which is made out of fluorides, and a low-temperature lubricant for cold starts, which is silver. And when we combine these constituents together in the form of a composite coating, we wind up combining their performance properties as well. And we have successfully lubricated bearings for over 100,000 startup and shutdown cycles from room temperature to 1200 Fahrenheit. Just to give you an idea of what that means, if we had a rotorcraft operating out of an airport doing 5 flights a day, 300 days a year, after 60 years, we would only have generated 90,000 startup and shutdown cycles. So we're truly talking about building a maintenance-free engine. Next chart, please. And this chart here shows photographs of this, what we call process bar. In order to deposit this coating, we take our engine shaft, we put a groove in the engine shaft to accommodate, have room for the coating. We sandblast the bottom of the groove to roughen it up to get a better bite and adhesion to the coating. Then we thermally spray the coating on the surface. That's basically where you take the powders, inject them into an argon plasma at high temperature. They melt, they splat, they stick, and you build up a thick coating. Then you grind and polish it, and that's your bearing running surface. I'll pass that around. Thanks. Next chart, please. Just to compare the performance of PS300 type coatings with foil bearings, the lower bar on this graph shows that we can operate from cryogenic temperatures above 600 degrees centigrade. Compare that with traditional oil lubricants, whether they're mineral oils or some of the more exotic synthetic fluids, even the fluorocarbons. They have a much more narrow temperature range. And that high temperature range is what is limiting some modern engine designs. We can't keep the oil cool enough in key locations. So foil bearing technology is actually seeing some early demonstration work in hot sections of engines. Next chart, please. Here's a photograph of one of our bearings in our test lab operating at 1400 Fahrenheit. Certainly, if we tried to use any kind of oil in this application, you'd have a fire on your hands. Next, please. And the nice thing about working for NASA is, on the one hand, we work on technologies that are 10, 20, 30 years out. We don't often see them get used. On the other hand, we're free to publish all of our information, and by getting the message out there that we've invented new technologies, sometimes they get picked up by industry, and it's kind of gratifying when you get recognized for this. In 2003, we received an R&D 100 award for our PS300 materials. We produced a variant of it that is not just a coating, but a solid form material. I've got that in my hand. This is a PM300, powder metallurgy bushing. It's a bronze replacement for motor bushings and conveyor bushings, and it's good to about 1500 Fahrenheit. This bushing material is in commercial use in furnace conveyors and has been for the last 5 or 6 years, saving industrial companies millions of dollars per year. It's also very worthwhile in the steam turbine industry for sliding mechanisms of control valves and things of that nature. So we've spun this technology off in the industry, and it's gratifying to see that we don't have to wait until we develop that new aircraft engine to see our technology paying off. Next chart, please. So we have the bearings, and we have the solid lubricants. We could just run in the lab and try them out, but truthfully, many have done that before, and we've broken quite a bit of hardware. We've got a third leg of our stool is analytical and computational modeling to try to understand what this technology is going to do before we actually do it. So we're talking about advances in finite element methods, rotordynamic analysis, where we're trying to determine whether or not a shaft system is going to be stable or whether it's going to excite itself and go unstable. Gas film calculations, what is the pressure inside of a gas foil bearing? What is the film thickness? Are we getting to a dangerous situation where the film is getting too thin and we're going to have a high-speed rub? If you're running a thin sheet metal foil bearing within a 10,000th of an inch of a shaft and you get a disturbance and you get a high-speed rub, you instantly melt all the materials that are in there. And so we see catastrophic failures, and they're not pretty. So we want to predict how that's going to happen. The technology is very robust if the system is well behaved. So we do analysis to try to predict things like bearing characteristics. That'd be like spring stiffness and damping characteristics of the bearing. We look at especially mechanical and thermal distortions. As shafts spin at high speeds, they centrifugally stretch. And as temperature gradients get into high temperature engines, you oftentimes will have localized thermal expansion and contraction. We want to make sure the bearing can follow the movement of the shaft and not bottom out anywhere. And again, we also look at rotordynamic performance. These foil bearings have very nonlinear stiffness and damping characteristics, and knowing how they behave under different vibration conditions can lead to more robust systems. The picture at the top right is the gridded out version of our oil-free turbocharger rotor, and the bottom left shows the centrifugal stretch of that shaft at 120,000 RPM. It told us that in the blue areas we were doing pretty good on a pretty flat cylinders for our bearings, but we had a high stress point right at the inside of our thrust collar. We needed to redesign it for that application. Just one example. Next chart, please. We do modeling. We do modeling of the foil bearing structure. Sometimes we do it independent of the gas film. In this case, we've modeled that bump structure as a top foil resting on top of a bump foil. Bump foil rests on a bump housing. So we're modeling it in a fairly simple fashion as a spring with rigid links for the foil stiffness. And we're also having to pay particular attention to tribology again, things like static and sliding friction for energy dissipation. And any of you who have worked with sliding components before know that it's very hard to predict exactly what the friction coefficient for first breakaway is going to be, and the friction coefficient at different conditions and different frequencies and displacements. So it's highly nonlinear. So we input values into these models like the bump pitch, the bump height, the spring stiffness, and our best estimates of the coefficient of friction. And these are the kind of modeling that we're doing to try to model different bump foil structures. Next chart, please. We also have to then model the hydrodynamic gas film pressures that develop. And this eye chart is not meant for you to be able to double check my equations to make sure I haven't left out a term. Quite honestly, this kind of stuff is beyond my ability. I've got colleagues that do this very, very well. But just to show you that we have to combine things like the Reynolds equation for lubrication, the energy equation, the structural equations, and combine all these things together coupled with that nonlinear structure. And quite honestly, this is really a job that's too big for even one research group. So we've got some collaborative efforts underway between NASA and university colleagues to develop predictive design codes for foil bearings with the expectation that those codes that will then be available for use by industry to be able to basically plug in a new design, get the bearing properties, put it in an overall system design, and see if the thing is going to work. Next chart, please. We also do modeling and analysis of experiments. Oftentimes we'll do experiments, get an unexpected result, and by modeling the unexpected result, sometimes we can figure out what went wrong, and from that learn how to avoid it in the future. We had a really interesting catastrophic failure of a foil bearing in a shaft in the lab, and I brought some of the damaged hardware with me. It's kind of neat. We were running a shaft on one of our test rigs with a business jet engine bearing mounted on the shaft. We were running at high speed and high temperature, but a fairly light load, and we were running at steady state conditions. That means we weren't touching anything. We ran for about 9 minutes, and the bearing catastrophically and unexpectedly failed. Just the rig came to a halt just like that, and we took the bearing off the shaft, and we'd actually melted a hole through the side of the shaft. Now this shaft is made out of Inconel superalloy. It melts at about 2,500 degrees Fahrenheit. We were running at 1,000 degrees Fahrenheit. We didn't really understand what happened, but we knew we had a high-speed rub in one location. Our first instinct was that we had a coating failure or something like that, or there was an inclusion in the shaft material in one spot and it broke apart at that one location, causing failure in one spot. And I'll pass this around now so you guys can see that. We put the rig back together with a new shaft and a new bearing, and we ran it again under the same conditions. It ran for 11 minutes, and it failed unexpectedly. Actually, it wasn't unexpectedly because it had happened at 9 minutes before. We took the bearing off, and again, a hole in the shaft right in the center. When it happens twice, you know there's something going on that isn't just materials related. We notice, if you look at this picture up there, that that hole in the shaft is at the same circumferential location as the little set screws that we use to balance the shaft. Just like on your car tires, you've got to put balance weights on your car tires so your steering doesn't shimmy. In the lab, high-speed shafting, we put set screws in the shaft at certain locations to balance out variations in how we built the parts. And that hole is lined up there, but the hole is in the center, not at the edge. So we had an event that we didn't really understand, but we knew we needed to do something to try to model and predict the shaft shape and behavior at high temperature and high speed. And being the keen senior government researchers that we are, we did what every other government researcher does under these same conditions. We brought in a grad student. In all honesty, we really thought this was a perfect opportunity to bring in a young person, teach them something about the oil-free turbomachinery, and utilize the most up-to-date modeling tools possible to try to figure out what went wrong. Next chart, please. And that grad student, who was now an Army Research Lab employee and doing a fabulous job, we set him to work to model the centrifugal stretching of the shaft because of those balance weights that we put in. And those balance weights go at the very edge of the shaft, so that the picture you see on the left that shows the centrifugal stretch and distortion, red means out around, out of the screen towards you. And the centrifugal modeling shows us that we should have had a bulge right at the end of the shaft. But that shaft passing around in the photograph, you notice that the bulge was in the center of the bearing. So we then went in the lab and we measured thermal gradients in that particular bearing under those particular conditions. And we noticed that the bearing ran hotter in the center than it did at the edges. That's not uncommon because in a foil bearing there's always air exchange from the sides of the bearing, and so the center is going to run hotter. But it's a band of heat in the center, and because the Inconel expands at high temperature, that hot thermal gradient in the center causes a bulge, a belly bulge if you will. But that hole that we had in the shaft was at one location. So when we overlaid the distortions, the thermal distortion and the centrifugal distortion together and combined them, we got the figure on the right, which shows a red spot right where the hole occurred, which was a bulge. And I've got, this is a solid model which was made up, which shows the bulge right where we found the melted shaft. And I'll pass that around as well. So you can compare those two together and see that we really did a good job of modeling it. The interesting thing is that this experience of burning a hole in the shaft occurred with one of our industry partners about a month after we finished this analysis. They were running an engine. They ran it for, I think, 7 minutes. It failed. They called us and said, "You'll never guess what happened." And we said, "Yeah, you burned a hole in your shaft." And we were able to explain why it happened. We told them how to do better cooling of the bearings and how to use a slightly thicker wall and get rid of the temperature gradients, and they ran the engine successfully. Next chart, please. And by the way, it doesn't always work out this well. So as those shafts pass around, think about how we experience something in the lab and that guides the modeling work. So it's not always just modeling, but you need that lab work. Sometimes the lab work guides the modeling work. Sometimes the modeling work guides the lab work. And this information helps us guide future applications. Next chart, please. We want to predict rotordynamic performance. And when I say rotordynamic performance, I'm really talking about, is the shaft going to spin stably and stay inside the engine where we want it without turbine blades rubbing against housings or doing other damage. So we model a shaft as a rigid link with a couple of masses we can place at different locations. And those masses are supported on springs, and the springs have dampers built into them, like the picture on the lower left shows. And what we're trying to do is predict critical speeds and natural frequencies. Sometimes we move the masses and the distributions around if we're doing design work. And we change properties of the shaft materials. We change rigidity. We change bearing stiffness and damping, all aimed at figuring out whether or not the system is stable. Now, a rotordynamic system, if you have a shaft, as it goes through its critical speeds, the shaft can bounce up and down as it's rotating. That's the bounce mode. It can conically pitch. That's the pitch mode. Those are rigid body modes. That's the shaft shape stays the same. And at very high speeds, the shaft can actually bend as it's rotating. That's called the bend mode. We try to model these things and come up with an operating map of where these modes occur so that we don't have an operating condition right over one of these modes. Next chart, please. Here's a model of a turbine engine shaft. I think this is from a T700 helicopter engine, showing how complicated the models can get when we want to model real hardware. It's not just one simple shaft with a mass on either end. This has multiple masses for the compressor section, multiple masses for the turbine section, and we'll spin something like this up on the computer with different bearing properties and see how it performs. Next chart, please. This chart shows a plot of bearing speed, or engine speed rather, on the y-axis versus bearing stiffness, spring stiffness on the x-axis. And those three lines there, the first and second rigid body modes are the low end, the pink and the blue. And the green line at the top, that's our bend mode. And what we want to do is pick bearing stiffnesses and operating speeds that keep us inside the safe range, the yellow area. Remember, I mentioned earlier, turbine engines typically run over a narrow speed range. In this case, the operating range is that little green box. Designers can look at that and they can see that they can change the bearing stiffness properties and not run close to a rigid body mode or a bend mode. We could change the speed range. Maybe we could lighten up the shaft and make it a little bit more flexible. That would move that operating range up closer to that bend mode. But this is the plot that a system designer would use to figure out how sensitive the system is to changes in bearing properties and shaft properties. And I'll just point out that most times when you're developing a new system, the plot doesn't come out this nice with all this margin around your operating speed range. Sometimes you run it the first time and you see your operating speed range is right on top of a critical speed. So it's kind of nice when you can do this and have some margin. Next, please. In addition to running on the computer, again, lab work helps drive what we're doing. This is a chart that shows up at the top left is a T700 helicopter engine. Just beneath it is the rotor simulator. That's that shaft. This time we've built it with masses on it that simulate the compressor and turbine. Sometimes we'll spin that in the lab and measure dynamic properties to get that critical speed map. One of the things we're doing most recently is we've actually gotten a hold of a used engine rotor with all the bladed components, and that's what that picture on the right is. It's intentionally blurred because there's some sensitive information that could be gleaned from that. But we're going to take a real engine shaft, we're going to spin it on foil bearings, and we're going to compare the dynamic performance of the real engine shaft to the dynamic performance of our simulated shafts that we usually use to make sure that we're getting similar data. So we have some physical basis and justification for using simulated hardware rather than using real engine hardware. Sometimes it's kind of nice to work on production hardware because you can actually get the real thing and test it. Most of our work is for future systems, and we have to sort of simulate and guess what it's really going to look like. Next chart, please. Another thing that we do is we look at bearing system level properties. This chart shows foil bearing tolerance to misalignment and trying to compare it a little bit to traditional bearings. We always say that gas foil bearings, because they're spring-mounted, have better misalignment tolerance than other types of bearings. We did some research recently where we actually proved this. We took a shaft, that's over in the middle on the right-hand side, we put it on foil bearings, we put it in the lab, we brought in a laser alignment system, and we aligned the two bearings perfectly. We spun the shaft up and measured its properties, and then we intentionally misaligned the bearing centers, and we ran it again. And we kept misaligning the bearing centers until we started to see distress in the bearings, temperatures going up, friction going up. And what we found is captured in this table, a little difficult to see, but for an angular contact ball bearing or a cylindrical rotor bearing, you've got to keep the thing aligned within a couple hundredths, maybe 2/100ths of a degree or so. The foil bearings tolerated misalignment 5 to 15 times greater than that. What does that mean for us in real terms? What it means is that maybe you can lighten up the structure of an engine so that you make the engine casing a little bit more flexible because you don't have to keep the bearing centers perfectly aligned for a spring-loaded foil bearing. So it's a new design freedom. Next chart, please. We also try to figure out how foil bearings are going to fail. Sometimes it's not just the shaft that fails. Sometimes the bearings fail because they overheat. That's kind of a foreign concept because I spent all that time explaining how you can run the bearings red hot. The bearings can run red hot at steady state conditions, but if they are continuing to get hotter and hotter and hotter, eventually they'll overheat. So you've got to carry some of the heat away, and we do that through conduction and convection with blowing a little air. But since air doesn't carry heat away as well as oil does, we've got to pay attention to heat generation in the bearings. And this chart shows power loss in a foil bearing as a function of speed, and starting at the lower left, when there's zero speed, there's no power loss. The bearing starts to rotate, it's rubbing, there's no air film, the friction and heat build. We get through a power loss maximum rather, as the bearing is just beginning to lift off. The gas film generates, the friction drops way down, and we get into what we call the desirable bucket, where that power loss minimum is. What we'd like to do is operate our bearing to the right of that power loss minimum, where the change in power loss as a function of speed is fairly broad, and faster speed increases the power loss a little more. That way, if you're running an engine and it slows down a little, the bearings get cooler, not the other way around. We try to avoid that steep region. Just try to keep in mind, power loss equals friction heating equals distress. Next chart, please. We took and sort of did a cartoon of that real data, and we plot here specific power loss in watts per square inch as a function of shaft speed. The red are the no-go areas. We found that we cannot cool a foil bearing if it's generating in friction more than 100 watts per square inch of heat. So there's a ceiling at the 100 watts per square inch line. We know we can't run a foil bearing below the liftoff speed where it's rubbing because it'll wear out the solid lubricants. So that's that line on the left. And we know we can't run so fast that the shafts come apart from centrifugal loading. So there's a shaft strength limit on the right. We put in our power loss bucket, and we kind of map out the undesirable operating points where it's very, very steep behavior, and where if you have a little drop in speed where things would get hotter, bearings get tighter, that slows the system down even further and you get a thermal runaway. We like to operate to the right in the desirable operating point range. So the concept here is a turbine engine designer would plot his idle speed and his operating speed on this characteristic line for the bearing that he's going to run and see where he is and how much margin he has. This doesn't go quite far enough. Next chart, please. We've since extended this concept to 3 dimensions where we plot power loss versus speed and load into the page and get a response surface curve. Now a designer can put runway shock loads at high speeds and low speeds. He can put maneuver loads at high speeds, and he can plot out where he is on that design operating space. This is very similar to what a compressor designer does when designing a new compressor for a turbine engine, where he'll have surge, he'll have different operating points and efficiency lines. All of these tools are here to try to guide application of this technology. Next chart, please. So we have these 3 key technologies, and the question is, how do we use them? Next chart. We have test capabilities at Glenn where we have bearing rigs, we've got coating facilities, we've got some oil-free engines that we operate for long-term durability, we've got the ability to run bearings at high pressure and low pressure, and we've got rotor rigs to prove out this bearing technology at a system level perspective. Next, please. We've developed a four-step application process where this is sort of a how-to. How do you develop a new oil-free turbomachinery system, where step one is doing a conceptual design, step two is doing bearing testing, make sure the bearings perform the way you expect. Step three is the rotordynamic system simulation to look at the system-level properties like misalignment, critical speed maps. And then step four is the oil-free technology demonstration. And what we've shown is that if you follow methodically these four steps in this order, your likelihood of success is very, very high. We've seen a lot of failures in industry over the years historically with this technology, and we find that they usually skip one of the steps. When we look at systems that have been successfully deployed, we see that the industrial counterparts, our colleagues in industry, have followed all four of these steps. Sometimes they don't follow them in order. They have failures. They have to go back and do a step over again if they skipped it. But this process works, and I'll show you an example of where it's worked. Next chart, please. We did an oil-free turbocharger. It was based on a truck engine turbo. This is a cross-section of the turbocharger. Two foil journal bearings, two thrust bearings, the NASA coatings. It was a hollow, rigid rotor. Next, please. You might be wondering why we did an oil-free turbocharger, and the reason is shown on this chart. If you think about it, a gas turbine and a turbocharger are very similar. They both have compressors. They both have turbines, main shafts, bearings. A turbocharger has a combustor of sorts. It's a diesel engine core. They operate at high temperatures and high speeds. One of the primary differences is the turbochargers are less expensive. So a turbocharger is a simplified, low-cost version of a gas turbine engine core. Next, please. We demonstrated this technology following our four-step process in March of 1999. This was a world's first demonstration. It had never been done before. And it was a team of NASA, Caterpillar, Borg-Warner, and Mohawk Innovative Technology. The picture on the lower left, that's a handsome young guy at the gas stand on that day in March of 1999. And I kind of expected the turbocharger industry to pick this technology up immediately. And like any other pathfinder or pioneering experiment that NASA does, sometimes it takes a little while for industry to catch on. Next chart, please. This chart is the front page of the very first production patent for an oil-free turbocharger. If you think about it, the work that we did in '99 was a pathfinder experiment. We showed industry what could be done. Industry began their own project based upon our work, and this patent is from Honeywell. They make half of the world's turbochargers. The patent was awarded in late 2006. It uses low-cost, high-volume bearings. In other words, the bearings designed for high-volume manufacturing. Industry funded it themselves. They had asked for our help from time to time, but they basically did it on their own. And this patent is their protection and shows how they overcame integration problems for putting this in automotive applications. The reason this demonstration and this patent is important is it shows how NASA technology gets into the marketplace. And one step further than that, this use of foil bearing technology in a high-volume automotive application will push the foil bearing technology forward much more than any government-funded program could do. So as millions and millions of these turbochargers hit the streets, people become familiar with them, more design codes, more technologists. It'll be that much easier to spin this technology back into helicopter engines. Next, please. We've also worked on foil bearings for very light jet applications. This particular application was a biz jet application where we developed a foil bearing for the core section of a business jet. The chart on the right shows how we tested it at ground idle conditions, at takeoff speeds from ambient to 1,000 Fahrenheit over the whole range of maneuver loads, and the bearing proved itself capable of handling the entire range. This engine did not go into production, however, come to the next chart, please. This bearing was taken from this project and put into the hot section of a Navy drone turbojet engine. This work was done by Williams International and Mohawk Innovative Technology. And if you go on their website, they talk in glowing terms about how well it worked. This is the engine that they failed the first time by burning the hole in the shaft. They don't like to put that on their website, and rightly, they probably don't need to. But it's a good example of where the government research helps the industry folks, and now they're taking this technology further and making that technology available. Next chart, please. So if we think about target aero propulsion applications, we've got rotorcraft applications, we've got subsonic jet applications, and higher speed flight like supersonic business jets and hypersonic jets. I just want to touch briefly on the value of this technology in other vehicle sectors. Next chart, please. If you think about a system benefit like weight reduction, maintenance reduction, heat rejection, and frontal area drag, that has different benefit levels for different vehicles. If you look for rotorcraft, I mentioned before, weight reduction is key, maintenance reduction is key, heat rejection not such a great importance. But in supersonic and hypersonic vehicles, things like being able to run bearings hot without necessarily a dedicated bearing cooling system is very, very important to high-speed flight. Reducing frontal area drag, very important to high-speed flight, as is weight reduction. So we're seeing this technology now placed in key locations in hypersonic-type flight vehicle propulsion systems. In terms of subsonic fixed-wing aircraft, the concept of building an engine that requires essentially no maintenance means that you could put lots of engines on a wing that were low-cost, line-replaceable units, and maybe enable things like blended wing body and distributed propulsion, multiple engines. Next chart, please. In terms of space applications, you knew I'd get there sometime. It turns out foil bearings got their start as the bearing type of choice for closed Brayton cycle turbines to try to avoid oil contamination of the high-temperature inert gas stream. This chart shows artist's conception of the Jupiter Icy Moon Orbiter and fission surface power, which is the project that's being worked today. Next chart, please. The concept here, which is shown in this schematic, is to use a heat source, either a nuclear reactor or a solar concentrator, to heat an inert gas. The inert gas goes through a turbine, comes out of the turbine, goes through a cooling system, through a compressor, and back into the heat exchanger, or even into a nuclear reactor directly. For this reason, oil lubrication, contamination of the working fluid, is not something that can be tolerated. The foil bearings, which can operate on the inert gas for these applications, is the ideal solution. And we've taken this concept even further than just the cartoon stage. Next chart, please. At NASA Glenn, we have something called our oil-free space power turbine demonstrator. We call it our dual-loop capstone demonstrator. And the schematic on the left shows the piping arrangement. The picture on the right shows it in the test cell. It's essentially two oil-free 30-kilowatt microturbines that have been modified. We took the combustor out and replaced an electric heater to heat the gas as the heat source. So the gas is heated, the hot gas goes through the turbine, generates electricity, then it goes through a cooler and it goes in a closed loop. The beauty of this system is that it's a turnkey system that you turn it on. As long as you're providing heat, the thing is going to run and generate electricity. There's no oil to change, there's no maintenance. So if you're going to do fission surface power and generate lots of electricity for years at a time without any kind of human intervention or maintenance, this is really a key technology. Next chart. So if you think about, what is the future? Well, oil-free turbomachinery technology has future applications in lots of places. Rotorcraft, where we've got the high temperatures and the high power density engines enabling new architectures. Next chart, please. Supersonic, business jets, fixed wing, hypersonic flight, all of them benefit from bearings that can run faster and run hotter and require less maintenance. And here's some examples of where you might see that technology, ranging from business jets that are in flight certification all the way to some concepts for blended wing body and hypersonic vehicles. Next chart, please. And finally, lest we forget the contributions that we can make in the space power and space propulsion arena, these technologies had their genesis in these space areas, and now that we've developed them further for other applications, we have the opportunity to reapply them in space power and propulsion to enhance that part of our mission. Next chart, please. So just to conclude, we've achieved breakthroughs and technology advances in the three key technology areas: We've developed and we've proven a method for technology application and transition. And the newly emerging oil-free products are going to form a strong foundation for advanced rotorcraft, fixed wing, space power, and many other applications. Next chart, please. I'd just like to thank you for your attention and also give special thanks to my oil-free research team, the Rotary Wing Project, Fundamental Aeronautics, and the folks at Glenn in the graphics office that helped me put this presentation together. Thank you very much.
Good afternoon. I'm Beth Dickey with NASA Headquarters Public Affairs, and I'll be moderating the question and answer session this afternoon. We do have someone with a microphone, so if you would please wait for that microphone, give your name and tell us where you work, that would be wonderful. Any questions here at Headquarters? Oh, we've got to have one. There we go, right here.
Yes, my name is Mike Dudley. I'm a detailee here at headquarters in ARMD. And you mentioned, or you discussed a couple of times, thrust bearings, but I didn't see the geometries for that. Could you briefly describe what the geometries are, and are there any significant limitations relative to conventional bearings?
Sure. The thrust bearings are actually, it's a very active research and development program that we have. The thrust bearings are essentially small wedges, and the wedges are made of small pieces of top foil with bump foils behind them, kind of like little ramps. And the thrust disc spins against those ramps and generates little pressure pockets that float the thrust bearing foils off the surface of the disc. Thrust bearings are a little bit different than journal bearings in terms of their performance. They generally have less load capacity than a journal bearing because there's more gaps in them. But on the other hand, in an oil-free turbomachinery system, it's not terribly difficult to use cavity pressure balancing to minimize the amount of thrust load that you need to support. So we've spent most of our time in the past 20 years studying the journal bearings because the journal bearings control rotor dynamics. We've now got an active program in thrust bearings to control the axial motion as well. The physics is the same, but the engineering is a little bit different.
This is A.J. Misra in the Fundamental Aero program. What are the major challenges in the foil bearing as you go from small engines to large engines?
I think it's a good question. These are not retrofit devices. If you really think about it in the most physics-based fundamental terms, the gas film is what's separating the thin sheet metal foil from the moving surface, the shaft surface. And that gas film has limits of how much pressure that you can generate because you can't run films that are too thin or you'll get rubbing of asperities. You can't run gas films that are too thick or you'll lose gas pressure out of the edges of the bearing. And so we're always working with gas pressures in the bearings on the order of tens of pounds per square inch, 50, 60, 80 psi. And so the amount of shaft load that you can support for a bearing of a given size is limited. In fact, the load capacity of a gas foil bearing is typically nearly an order of magnitude lower than a traditional ball bearing of the same size. However, as the speed goes up, the load capacity of the gas bearing gets higher, the load capacity of the ball bearing drops. And so what you have to do is not think about taking a large engine as it currently exists and taking the ball bearings out and putting in a foil bearing of the same size. You have to think about redesigning the engine itself, perhaps having an engine with a smaller compressor and a smaller turbine that runs at a higher RPM that has foil bearings that are a larger diameter. So we're not advocating taking a Pratt & Whitney 4000 or a GE 90 engine and making it oil-free. We're really interested in seeing how far we can push the foil bearing technology in high-speed engines that are maintenance-free and possibly using multiple engines in place of one or two large engines.
Any other questions here at headquarters? Up in the back?
Are you looking at magnetically suspended bearings as another way of avoiding oil?
Yeah, that's a
And
very...
how does it compare to
That's a very good
technology?
question. There has been a lot of active research in electromagnetic bearing support for the past 30 or 40 years. And in fact, we had an active program in that at NASA Glenn for some time. The main emphasis at NASA is high temperature and flying these bearings. So weight is critical and volume is critical. And what we have found with the electromagnetic bearings is that there are really significant benefits to being able to control actively things like stiffness and damping and shaft position of a bearing. And you can't really do that with a foil bearing. It's a passive device. On the other hand, if you're going to fly a bearing technology, it has to be small and lightweight and reliable. And what we've seen in the electromagnetic bearing industry is that that technology is making tremendous inroads in terrestrial applications, in power generation systems and gas compressors, where weight and volume are not issues. But in flight systems, it cannot be the sole source unless there are tremendous breakthroughs in power density and in load capacity. What we've been advocating for quite some time is that you marry the technologies together. So you'd have an engine shaft that would have the gas foil bearings in the hot locations where you can't take the heat for the mag bearings, and maybe you'd have somewhere in a cool section a magnetic bearing which is also doing double duty as an integral starter generator and maybe as an active damper. So I see the future of these technologies kind of merging together, where you'd have a small magnetic bearing that would float the shaft during startup and shutdown, so you wouldn't need as much of a solid lubricant, and providing generation capacity on the shaft. So it's not really an all or nothing thing, as some might think, but really where the future rests is probably a marriage of those technologies.
And our next question's right over here.
I'm Brad Carpenter with Space Operations. These designs all use shaft motion to entrain a lubricating gas motion.
That's a good way to put it, yeah.
But would you enlarge your performance envelope at all by introducing a forced gas flow?
Yeah, what you're talking about is hydrostatically floating the shaft, and we have done work with what we call hybrid foil bearings, where you have a gas bottle or a compressor and nozzles that float the shaft to add some load capacity. And that concept works. Unfortunately, you pay a penalty for efficiency by having to pump extra gas into the system. And if you try to do too much of your load support with pressurization, you get into situations of instabilities, gas instabilities like pneumatic hammer, where the shaft will actually start bouncing around because it's pressurized. So the hydrostatic concept, again, intuitively, it looks like it would be easy, but you don't have much damping coming out of the gas film. We use hydrostatic bearings that are oil lubricated because if a shaft tries to go unstable and bounce around, the oil forms a squeeze film cushion and damps out the vibration. But with a hydrostatic bearing where you're pressurizing it, you can really get it bouncing around pretty heavily.
All right, now we'll take a question from NASA's Glenn Research Center. Glenn, go ahead with your question.
I'm wondering about whether you have studied the composition from a material standpoint of the foil bearing materials, and are there advantages to using materials of different composition?
That's another good question, and I wouldn't want to take credit for that work myself, but if you do a historical retrospective of the foil bearing technology, you'll see that the earliest foil bearings were made out of plastic acetate film and magnetic tape. Then people were looking at copper alloys, copper beryllium, because the high thermal conductivity gave the bearings a really robust performance. We've been concentrating on the Inconel superalloy material because we're always looking for high temperature spring properties, but certainly for lower temperature applications, other materials would probably work well. You need a combination of fatigue resistance in bending. You need spring properties, especially at elevated temperatures. You need to be able to form smooth foils at thin enough layers. But I think the field is wide open to looking at new materials for foil materials.
Do we have any other questions here at headquarters? All right, then, we'll call it a briefing today. For information on this topic and other NASA topics, please go to www.nasa.gov or www.aeronautics.nasa.gov. Thank you for being with us today.